unsteady aerodynamics. And this will go for maybe several lectures, because we will formulate the unsteady aerodynamics and how the final expressions are applied for the dynamic aeroelastic calculation. That will come at the end of the course. Basically, in aerodynamics, we need 7 quantities. These 7 are density of, then pressure, and 3 velocity components, u, v, w. These are velocity components. Okay. Then temperature, and viscosity. Okay. So essentially you have 7 quantities at any point in the fluid. Non-reacting fluids, that's what we are taking. Now, if you have 7 quantities, you need to have 7 equations. Okay. Now, those 7 equations are, I'll just write the names. You have one is, all of them are from conservation, mass conservation, which is continuity equation. Continuity equation. This is basically mass conservation. Then you have momentum equations. You will have 3 equations. This is one equation, because 3 directions. And then energy equation, which is the first law of thermodynamics. First law of thermodynamics. This is one equation, energy equation. Then you are dealing with air, there is gas. So you will have equation of state. This is basically the gas law, perfect gas, you may assume ideal gas. 1. So you have 6. And the 7th equation is empirical relation of viscosity, okay, with temperature. How viscosity, forget about viscosity as a function of pressure, you neglect it. It's only viscosity as a function of temperature you take. Now these equations are, some are differential equations, some are algebraic equations. So you need to solve these equations with, of course, there are corresponding boundary conditions. That is what your complete aerodynamic theory is. But if you take these 7 and these 7, this set is called the Navier-Stokes equations, NS. Navier-Stokes, okay. Full 3D problem you can solve. But then what we do, if you make some approximation, okay, the first level of approximation is, this is the full set, 7 unknowns, okay. That's what CFD people, direct numerical simulation or something, take all the 7 equations and then start solving Navier-Stokes equation. But you make one approximation, first level of approximation, which is, I say that I neglect viscosity. That is, neglect viscosity. Okay. When you neglect viscosity, what will happen is one of the variable drops out. Okay. And you will have the Euler formulation. Okay. Here we start. Okay. Euler formulation. Now we are not going to do this Euler formulation also. This can be further simplified, okay, which is called the potential flow. Okay, that is what type of approximation you make to reduce from here to the next level. This is, you make, this is no viscosity, that is inviscid. You make inviscid and isentropic. Okay. Okay. You make these assumptions, then you will get the full potential or full potential equation or potential flow. You may call it potential flow. Full is okay, it may be fully nonlinear. Then you make further assumption that is a small disturbance. Okay, you will get linearized potential flow equation. Okay, that's all. Now what we develop in this course is only the potential flow, and finally we will do the linearized potential flow equation. That's what we will solve. But of course, depending on the problem, you have to choose, because today people are solving in the CFD. In CFD this is also used, potential equations are also used in CFD problem. But now people will go for Navier-Stokes or Euler formulation, various types of formulation. But we want for our aeroelastic formulations whether we can get a closed form solution, even if it is approximate, and use that for our aeroelastic calculations for particularly unsteady conditions. Okay, that is the idea. So we will develop the potential flow equations. So how do we start? Where do we start? We will go through one by one all these equations: continuity, momentum, first law of thermodynamics, equation of state, everything we will write. And all of them later we will reduce by using some assumption of irrotationality condition. And then it will come as a potential flow, means basically my velocities are derivable from a potential. Okay. Then I will have actually only one equation for potential, and of course there will be another equation for speed of sound. Okay. These two will be there. But if I make further assumption incompressible flow, then you will get further reduction in the formulation. But all are unsteady. Okay. Then you have to apply the appropriate boundary conditions. So what we will do is, since it is going to be highly mathematical, please understand, because here it will be a lot of substitution and then simplification, etc., etc. It will look like highly mathematical. invariably people will get lost in the math to know what is that we started with initially. Okay, that is missed, and you will go in algebra, jugglery, substituting this, substitute. Our aim is getting ultimately, please understand, this is what we need. Okay, and we need to develop the equations based on simple mass conservation, momentum conservation, which is basically Newton's law, and energy conservation, which is the first law of thermodynamics. Okay, and then of course we apply these isentropic relations, isentropic conditions. Okay, so always keep in mind that our aim is to get this, because viscosity we neglect, inviscid. But then the applicability of whatever the potential flow, it is fairly good for most of the flows, except that when you have a very strong shock where there is a heating happens, then these equations are not valid. This solution is not valid. But still, people use potential flow for transonic also. Please understand, the industrial codes are based on their last one. Okay, for aeroelastic analysis. It's not that they do Navier-Stokes work. People are developing it. That is a different matter. But it is still a field of research completely. Okay. But for aircraft wing and other things, they have developed a potential flow, which is, I will briefly describe, but we will not be getting into that because these are all research publications. Okay. And people have developed the code. Ultimately what we want, and wing is vibrating, I want to know what is the pressure at every point on the wing. If I know the motion, what is the pressure? What is the pressure? I will get the motion. That is the relationship. Okay. So ultimately the boundary condition will be on the aerofoil you apply because it is moving. Okay. Now let us start with the basic equations. What are the ingredients which we require? And the first one is Gauss theorem. Okay. So it will all look mathematical for next several lectures, but don't lose track, because this is invariably people lose track. Our aim is ultimately to get these things. Okay. So since the lectures will go on for the formulation, will go on for several things, because this is normally not covered in any of the aerodynamics course. Okay, they don't teach this part. That's why I thought I will cover this. Okay, you have Gauss theorem. Gauss theorem, or it's also referred as divergence theorem. This is basically, it states this is a surface integral over an area is a volume integral del dot V dV. Or you say del dot V is, you write it as divergent V, which is a scalar. Okay. This is a Gauss theorem. Now the proof in the fluid mechanics, normally it is taken as, you choose a control volume. Okay. That is, you define your axis system and then you take a control volume. Okay, the velocity at this point is u, v, w, and you say this is delta x, this is, you may say, delta y, and this is delta z, and you calculate what is the net outflow through this small elemental parallelepiped. Okay, the velocity here, you write it as u plus half delta u by delta x, and on the back face, because this is at the center point, on the back face you will have u minus half Similarly, you can have all the 6 faces. What is the flow? Into that, what is coming in and what is going out. If you calculate what is going out is this velocity times this area is out, minus this velocity times the same area which is coming in. So if you find the net outflow will be delta u over delta x plus delta w over delta z. You will have delta x, delta y, delta z. Net outflow over this elemental parallelepiped. Now per unit volume, if you take net outflow per unit volume, this will be, you divide by again delta x, delta y. That means what we have obtained is whatever velocity into area is nothing but del u, del x, del v, del y for that volume. Now if you assume some control volume, you say, and you divide this into several blocks, small blocks in the 3D. Okay, so whatever is coming in here for this cube, whatever is going out, that is nothing but what is coming in into the next element. So like that, if you keep the whole thing, finally it will be basically whatever is, this will become V dot N. You may say dA, dA is the small elemental area. This you have to integrate over the entire surface. The surface will be, so this will become surface integral. And then here, this will be del dot, because you said that whatever is coming in is nothing but this. In the limit of, if you have unit volume is this, multiplied by that into the elemental volume, integrate over the full volume, you will get over the full volume. This is nothing but del dot V dV, because this is dV. Okay. So this is your divergence theorem, and that is what we have written as a dV. Okay, you can use the lowercase v or capital V, whatever, but don't put a vector. Okay, this is the first theorem which you use it for divergence, but then there are modifications of the divergence theorem, which you can give it as a proof, but I am writing it only A B dot N dA. This becomes volume integral of A del dot B plus B dot del A dB. Okay. Del operator, you know that I delta by delta x, I plus j plus k, that's all. These are all unit vectors. Okay. And then the other one is C, which is a scalar, N dA. This is gradient C dV. Okay. So these are all modifications of the same thing. Okay. What I would say is you prove this using this, and similarly this also, C is a scalar, you prove this also, very similar to this. Okay. Now we will be using all these three relations in our development of equation. That is why the very first thing is you develop this basic equation, which is the Gauss theorem. Okay. Now let us go to the actual equation formulation. Okay. Give a very general see, mass conservation implies that the mass, if you fix, this is, you look at a quantity of fluid which is here, okay, and you track this. Please understand, you are tracking the fluid. That means you are looking at the mass wherever it is going. The other one is, you look at a region. You are not bothered about what is happening to a mass, you are only looking at a region. So the region is a controlled volume. But mass conservation, you can apply only to some specific mass. Okay. But how that mass conservation is related to a controlled volume or momentum conservation, because momentum conservation is again what? You want to know Newton's law, F is equal to ma. Mass is fixed, force is applied, okay, and what is the acceleration of that mass? Now this is for a fixed mass, you are looking at that, tracking the mass, but how that gets related to a control volume later. That is what I will give you one general proof, and with that you can write all the three equations, actually all the four, continuity as well as momentum. Every equation will come out from one generic formulation. Okay. So let us say this is the quantity of fluid at time t1, and at time t2 this has occupied this space. This is at time t2. The same fluid has come here in that dashed space. Now let us divide this whole thing into space A, this is space B, this is volume C. Okay. You need to know any property. Now I am going to say the property of the fluid which is final minus initial. The property per unit volume. If I take, suppose if I take density per unit mass, if you want you can take per unit mass also. Rho is the density, which is mass per unit volume. Okay. So let us say rho is now I want to know a property of this mass, how it is changing. If it is unity, how the mass is, that is mass per unit volume, how the density is changing. But if I say velocity, then you say it is a momentum. So I am going to write only a property which is B. P is the property. It can be one, it can be velocities. So when you write it as just P, rho P. So what is that initially? The change in the, let us write change in over change in property. Okay. This is a elemental volume. Please understand, this is an elemental volume. You can integrate and you will get it. What is the initial and final property? Rho P at B in time t2, because B is this, please note B is the common volume, plus rho P at C T2. Okay. Minus, this is the final value, because what was originally in this domain, that continuous domain, it has now moved here, and I am at time t2, whatever is the property is B at t2, C at t2, minus rho property P B at time t1, minus rho P A at t1, 1 over delta t. This is the change in time. Now what you do is you add and subtract two quantities, rho P B T2 plus rho P A at T2, okay, minus rho P B at T1 plus rho P at A T1 plus rho P C at T2 minus, because I have added this rho P A2, so I will subtract rho P at A T2 and divided by 1 over delta T. Okay. This is over the entire full volume. If I take it, this is for a small element. If I take the full volume, I will have to only integrate. Now you know that 1 over delta T, this quantity, if you look at it, okay, this is nothing but I am looking at this control, this volume, the continuous line, what is happening in that small elemental change in time. That's all. That means this is the time variation of the property rho P in the limit delta T tends to 0 over this control volume. Now what is this quantity? Rho P C T2 minus rho P A T2. That means this region, whatever has come in, because this surface has gone out here. Similarly, this surface has gone out here. Okay. So this is like what has flown out, you can say, because what this is flowing out minus flowing in. So net flow out. So this change in the property, if I look at it from a control volume point of view, this is nothing but the change. This will be volume integral. Now this is the control volume. Delta rho P. dV is the volume, plus surface integral rho P flowing in, that is velocity. I need to have Q dot N dA. This is over the surface area. Okay, a surface area. But please understand, I am putting delta by delta t within that, not outside. Okay, this is the property which is changing with time, and this is the property that is flowing up. So this is what your change in property of this mass. Please understand, change in property is a total. I am looking at this, tracking some mass, okay, but that is related to the control volume here. Now we will derive our three equations right from here. Suppose if I say my property is, can I erase this part? I will erase this, this is not necessary. Okay. If I say my property is mass, mass is what? Change in mass is, so change in mass is 0, it cannot change. Okay. So if it is mass, if my property P is 1, change in property is change in mass. Change in mass is actually 0 because the mass cannot change on that whatever I started with. Therefore 0 equals what? Delta by delta t of rho, because property P is 1 into dV plus rho q dot n dA. This is 0. Okay. Change in property. Now you can convert this into look at this equation, because rho is a scalar and the rho q is basically the vector quantity, vector dot nda. I can convert it into a volume integral which is divergence of that. So which can be written as 0 equals volume integral, I will write it in 1 delta over delta t rho plus this is del dot rho q dV. Okay, since rho q is my vector. Now the volume is arbitrary because I can choose any volume I want. Then automatically the term within that integrand has to be 0. Okay, and that is my continuity equation, which I will write it here as delta rho over delta t plus divergence of rho q. Okay, this is my divergence equation, which can be written in a slightly different format of, you expand this, this can be written as delta rho over delta t plus rho del dot q plus q dot del. Okay. And this particular term, I think not this term, sorry, these two, this and this, they combine it and write it as okay, delta by delta t plus q dot this particular term people use the substantial derivative or total derivative or whatever, okay. But basically it doesn't matter. You can use it this form, this form, this form, this form, any form, it doesn't matter. Okay. Now if my density is a constant, constant means anyway it doesn't vary with time. Density is a constant, it is incompressible. Then del dot Q is 0. Okay. That is the incompressible flow, but we don't have to use it. We will keep it as it is. Compressible flow we will keep. Okay, now this is my continuity equation. Okay, now keep this equation because we have to use this again. Okay, now possibly maybe I should write it in one corner and we will have that equation later when we substitute. So I can write it del rho over delta T plus rho del dot Q plus Q del, this is 0. Okay. This is one equation, continuity equation. Next is, so this is written as total derivative, material derivative, substantial derivative, all. Basically this means this. Okay. Now I will erase this part. Let us check the property P as velocity. That is conservation of momentum. If P is my velocity vector, P, now that equation will be the change in property, whatever, because this is mass into velocity is acceleration. Okay, so acceleration is equal to the force that is acting on that, mass times acceleration. So you will have, this is the volume integral, delta by delta T of rho Q dV plus the surface. This is rho Q dot N dA. This is your external force which is acting on the that mass. Please understand. The external force you can have it as two. One is the pressure, another one is the body force. Okay. So the F, I will write it here. One can be a body force. Body force means it is a volume. Rho F dV. This is the body force. And then on the surface you can have the pressure, but the pressure I am taking it acting in the opposite to the normal. So I will put it minus P and dA. Okay. Now you see I don't have any surface shear force. Okay, that is where I neglect the viscosity. You follow? Otherwise if I have shear, you have to put that viscous thing will come. So I don't have any viscous force. So there is no surface shear force acting on this. Now this again what you do is you transfer it to this side. This surface integral you convert it into volume integral. That is using this relationship. Okay. The second one, because you say this as rho Q is A, Q dot N is Bn. Use that relationship, and then this is pressure. Pressure is a scalar quantity. Scalar N dA, that last relation. C and dA is gradient C dV. Now convert all of them into volume integrals. Okay, if you convert all of them into volume integral, you will get like this. So I will write the full stuff. Delta over delta T rho Q plus rho Q del dot Q plus Q dot del rho Q plus delta P gradient minus rho F dV. Now you say, since I have actually taken these terms to the left hand side, you see this term gets converted by that second. That is why I keep writing that, because you have to keep that. How you get everything getting converted into another long expression. Okay, now since the volume is arbitrary, therefore this quantity must be 0. Okay, this quantity you can write it in delta, you can write it in two form. What you do is rho del Q over delta T plus Q, I open a bracket, delta rho over delta T plus, please understand, this is this term. Okay, here I have taken Q outside, so I will get rho del dot Q. Here I have to split it into two parts. One is I take rho in the derivative, another one rho treated as a constant, del Q I will take it. Okay. Now when I take that, I will have Q dot del rho plus, because this I am taking two terms, the second term will be rho Q dot del of Q. You will have pressure term minus plus del P, you can take it, minus rho F. Now if you look at this particular term, okay, this is nothing but my continuity equation. Okay, therefore this is identically 0. Okay, this particular term. Leaving behind, I now erase this part. Okay, you will have rho del Q over del T plus this term rho Q dot del Q equals, I am taking minus del P plus rho. Okay. Now what you do is, if you neglect the body force, usually the gravity, body force, you neglect it, so this term goes to 0 and your rho is common. So what you will get is, you will write this equation as delta Q over delta T plus Q dot del Q equals minus delta P over rho. This is my momentum equation. That's all. Okay. Now this also you can write it here. So you have continuity, you have momentum. Momentum you can write it as, you see, that is why delta by delta T, q dot del, q you can take it, that is the total derivative or substantial derivative or expression. So you will write it as delta q over delta t plus q dot del q equals minus delta p over. Okay. Now please understand what are all the assumptions we have made till now, because that is essential. So don't lose track of any assumptions which have been made in obtaining this. First is we neglected the viscosity and we neglected the body force. Okay. Now you got these two equations. Velocity, we have, see how many equations are there, how many unknowns. We have, this is a vector equation, please understand, because this is a gradient. Gradient means ijk. Okay. So you have three equations here. This is one equation because this is the delta rho, delta q, delta del, one scalar. So you have one equation here, three equations. So you have four equations here already. But the variables are density, q is three velocity components, q is a vector, u, v, w, and then pressure. Okay, so you have five. Alright, you have five unknowns here, but four equations are over. Now you have to get the fifth equation, and then from there we will try to reduce something. Okay. First we will write the equation of state, then we will use the energy equation. That is the first law of thermodynamics. Okay. Now I erase this part. Because the equation of state so we have to take it the, we are bothered about only air. So we say the condition is not very high, it's a cold air and the properties do not change, that is the chemical composition or physical composition, they are same, there is no intense heating. Okay, because everything will change. So the thermodynamic characteristic, because we are going to assume ideal gas law is valid. Okay, ideal gas law or perfect gas law. Okay, P is rho r T. R is the gas constant, T is the temperature absolute. So you see this relates pressure, density, temperature through some gas constant. You can get it related to universal, otherwise for dry air it is 272, some number is there. Okay. Now this is ideal gas law, you think it is applicable. Okay. And that is the key. You have to assume that it is applicable for our equation. Then you also say this, if you assume the gas is, this is called ideal gas or thermodynamically perfect. Okay. You can normally perfect gas, they say perfect gas. But in addition, you have two quantities which are the Cp and Cv, okay, which is basically specific heat. Okay. At constant pressure, at constant volume, they may be functions of temperature. but then we are going to assume that they are constant. They don't vary with temperature. And then you have Cp minus Cv, this is R, which is the gas constant. Okay. If you assume that these two are independent of temperature, okay, then this is called calorically perfect. That is Cp, Cv are independent of temperature. Then calorically perfect. Okay. So we assume both. Alright. Our gas law, these are valid. Then you go to first law of thermodynamics. Because you know that Cv is related to internal energy. Because change in internal energy is directly written as Cv times delta T. In a small change in temperature, internal energy changes by Cv. This is to enthalpy. Okay. So now I will not get into that. We will just describe very simple terms. First law of thermodynamics. That is, if you add heat, the heat goes towards doing some work and some part goes towards increasing the, you can say, internal energy of the system. So heat, you may write it as dQ. This is the heat, but I am using the quantity Q. Please understand, this is heat. This Q is not velocity. This I am writing it as dU. This is internal energy. This is change in internal energy. Plus dW, because this is a, you call it as a exact differential. Okay, because U1 minus U2 you can do this, but this is the work. There is nothing like W2 minus W1 work. Work is work. Quantity of heat is how much you supply. There is no, some exact differential is not there. That is why this capital D is used for this. Now here we have said that it is calorically perfect, ideal gas, everything. Then basically dU is Cv into dt. Okay. Okay. And dW is P. This you can take per unit mass. Per unit mass, if you write it, then you substitute. Here what we are going to assume is, then you can write V is 1 over rho, because this is per unit mass. Okay. Or dV becomes d over 1 over rho. Okay. Unit mass. Of fluid. Now you start making assumptions that heat, I am going to say I am not adding any heat. Okay, this is an adiabatic process. That means dQ is 0. Then I also impose the condition that is it reversible or not reversible. Okay, because then it is only one way. If it is an irreversible process, I can have an adiabatic, but it can be irreversible. But I am going to assume it is also a reversible process. Okay, therefore this is called the isentropic. Adiabatic, reversible. Please understand, I am going to assume adiabatic and reversible. isentropic process, which means my dq is 0. I will write the equation in this form: 0 equals cv dt plus pressure is dw is pdv, p is rho rt, dv is 1 by rho. Okay. Now this equation I write it in this fashion: cv dt over t, because I divide by t, plus rho r, df 1 over rho will be, we'll have minus, okay, so this rho will cancel out, so I will be left with cv dt over capital T minus r d rho over rho. Okay. Now this can be, you take it to the left hand side and write it as you can put it in simple form, that is ln something. I will bring that part for that sheet. Okay. That is, I will write this as differential of ln, please understand, t power cv rho power minus r. This is 0. Because I take it, I integrate it, and then I am writing it. That means ln of this is a constant. Okay, so I will write that ln of t power cv rho power minus r. This is some constant, that means this is a constant. So I will write t to the power cv divided by rho to the power r, a constant. Now what you do is, you again, this can be, it's just algebra only. I will show that this is t over rho to the power r over cv, because I am taking 1 over cv, which I am writing it as t to the t over rho, r is cp minus cv. So I am writing cp minus cv over cv, and I am going to call ratio of specific heats cp over cv as gamma, and I will have t over rho to the power gamma minus 1. Is this a constant? And what is t? T is p by rho r. Okay. So I am going to write p over rho r 1 over rho gamma minus 1 is a constant, and r is a gas constant. Therefore I am going to get p over rho to the power gamma is equal to a constant. Okay. Which says pressure, or you can say density, is only a function of pressure. Okay. Density, rho, is a function of pressure. Okay. And this type of fluid is called the barotropic fluid. Okay, it's called okay. That's all. Now P by rho power gamma is a constant. Okay, now I have 1, 2, 3. P by rho power gamma is a constant. Okay, but this will, please understand what assumption we made. It is an isentropic flow. That means no heat is added and it is an adiabatic process and constant entropy, reversible. Usually this gets spoiled only when you have a strong shock, because shock, there is a heating, local heating. Local heating, it gets disturbed. That is why this will be valid even up to Mach 0.3, something like that. You can use it. Only when you go to very high Mach, very intense heating is there, then this theory fails. Otherwise, normal supersonic flow 1, 2, you can use this potential flow theory. Okay. There is absolutely no problem in using, and this is what is used in most of the aircraft industry. Of course, CFD is progressing. I am not saying that CFD is not used, but that is progressing. But even CFD, potential flow, because you can't get a closed form solution always for this equation. Okay. Now P rho to the P over rho power gamma is a constant is another. That means I have a relation between pressure and density. Gamma a constant. So essentially you have 5 equations you obtained. Actually these 5 are sufficient to solve. But once you solve this, if you want temperature, you can go back here to get the temperature. Because temperature doesn't come explicitly in these 5 equations. Now even these can be further simplified. Simplified in the sense, it's not that I am neglecting anything. I will reduce them by introducing the concept of irrotational flow. Okay. So, but before we go to irrotational flow, we have to define a few things. So we will say irrotational flow. Because these 5 unknowns, 5 equations, you can use them, but they can be reduced if you introduce the concept of irrotationality and also a velocity potential or acceleration potential. We will define both of them later. But right now, let us define something called as circulation. Okay. Circulation, gamma, is defined as over a closed contour q dot e r. Please note this is velocity or the element. You have to integrate. Now, let us, for the sake of calculating this in the 2D, you take a point, you take this. This is uv, this is delta x, this is delta y. Okay. Now you want to calculate circulation. For this element, you will have, this is in this place, you have to go like this. At the top of the so you will have u minus y, delta u over delta because the velocity here, this is the velocity at this point. So velocity here u along x is u delta u by delta y divided by 2 into, here you will have what the velocity is v, you will have plus v plus delta v over delta x over 2 into delta y. Then here the velocity will be this way, so you put a minus sign. So you will have minus of u plus u delta u over delta y delta x, and again minus of, because here the velocity is this way, so your integration path is this way. So you put a minus sign, v minus delta v over delta x. If I take this quantity, you may call it d gamma or gamma over a small element, that will be minus, you will get this is minus what? Delta u by delta y. This will be plus v by delta into del. This is the area of the. Now this quantity is nothing but, if you define curl is curl q is del cross q, that is nothing but the kth component. You will have I delta w by delta y minus delta v over delta z plus j delta u over delta z minus delta w over delta x plus k into delta v over delta x minus delta u over delta y. Okay, this is curl q is this. Now if you say this is the area dA, normal to that is the z, okay, which is nothing but the normal component of curl q. Normal component means you take actually to that area. Whichever area you are looking at, take the normal, and that normal component of that curl is basically this circulation. So if you define each one of them as, you can write this as omega. Curl q is a vector omega which is curl q, which has omega xi, omega yj, omega zk. Okay, you can define now, I erase this part, that is curl q, a normal component, because n is, you take a define a normal, that is equal to, you say q dot dr over, because I divide by delta a, this will be delta a, because I am dividing, this is what I am getting. This delta a I can take it here and take it as a normal. So this will become curl q dot nda. Okay, this is nothing but integral q dot dr over that small part, this part. Now if you define a larger area, you can divide it into lot of regions. Every region you will have, this is going. So you will find this will cancel with that, that will cancel with that, leaving behind only the boundary part. So boundary means this itself you can take it as a over a full surface. This is over the complete outer boundary. Okay. Now this is your Stokes theorem. Okay. Now Stokes theorem essentially relates, please understand this is a surface integral to a line integral. Okay. But the curl Q is Q dot dr. Here we say divergence theorem is surface integral is getting into volume integral. Okay. Now let us define one more. So this part is over. There is some theorem, another theorem which is called the Kelvin theorem. Okay. What does the Kelvin theorem states? Okay. If the flow initially is irrotational, okay, that means it is del, that is curl Q, okay, del cross Q. If it is 0, this is nothing but curl Q. Okay. If it is initially 0, it is 0 always. Okay. The flow remains irrotational always. Now, how do you justify this? This is a question. Suppose the flow starts from a reservoir. We always say from a reservoir. The flow initially far field, somewhere it is starting, like a wind tunnel or anything. It comes with a uniform velocity. Okay. Everywhere. Then automatically curl Q is 0. Okay. If it is 0 initially, then it continues to be 0 always. Okay. Now this has to be, of course, you have to prove that. Okay. Because you say gamma is integral what? Q dot dr. Okay. This is defined over a closed region. Okay. Now how do you say this will be 0 always? Okay. Now this is where the proof starts. Here is this part that we have. And maybe this we can start next class because I think this part I will do because now it is. If I start, I don't want to leave it in the middle. It will take some time.